All right, so we finally have made it to discussing probably one of the most misunderstood concepts in all of calculus. And for some reason, a lot of students have said to me before, this is a confusing topic, but then after I teach it to them, they're super excited and it makes a lot of sense. And so, we're going to hopefully spend this video building an intuitive understanding of what's going on to hopefully make sure you all walk away with that feeling of just kind of understanding what this concept is. We're going for conceptual understanding and a little less about, just doing as many examples as we can, because number one, the book has a bazillion examples, and number two, in general, like setting up these problems and understanding what they're asking is going to lead to a better sense of understanding when it comes to what we're going to be doing next week and the week after that. So let's make our primary focus to really understand the goal of this section, which is what is a line integral. And I think the best way to do this, is to simply start with a sketch and to give you all kind of a visual interpretation of this. And I will do kind of a couple little sketches here to kind of iron some things in. Okay, so perhaps as a brief recap, even though these things should be pretty well known in your vocabulary at this point, a regular double integral, takes some function, right? It takes a 3D function, f of xy, and it integrates over some domain, right? Some region, which we call R, like this. And we add up all the values of the function over that region. What does it look like in 3D? That region is sitting here on the xy plane, and that function is, some 3D function, f of xy, and it gives us kind of volume, if you will. It's like the volume over this shape, but I've always encouraged you not to really think about it like that, and to just think about, if this function represents, the heat at every single point in this region, then it's going to give you the total heat. If it represents the probability of something happening at each, input in this region, then it's going to give you total probability, and so on and so forth. The concept, when we think back even further back to just regular one-dimensional calculus, of having some good old-fashioned, two-dimensional function, and let's say we want to integrate it over some region, that was a one-dimensional region here from A to B, and we had our function, and again, we thought about it as area under the curve, and we were adding up all the values of the function for every single point in this region. And so that's how integration has worked so far, and that is how it will continue to work. But let me posit a slightly different scenario than the ones that I have just given you. So let's imagine that we have some race track, okay, and it looks like this. It looks like this parabola, f of x equals x squared, okay? And at every single point on this track, from x equals 0 to x equals 1, a car is driving, and then it is driving in a particular direction. It's driving in that direction. And so my question is, if at every single point that car is making progress, and it's expending a little bit of force, say, right? It's working a little bit to do some movement. And hopefully we remember back from Calculus 2 that if we add up, kind of like the total force over some little distances, this gives us the work done. Okay. Now this was easy before when something was moving in a straight line, but what if it's moving over a path? What if we want to integrate, we want to add up all of these little values, all of the little bits of energy, the little bit of force that the car is exerting from 0 to 1. And I'm not talking about area under the curve. I'm talking because I'm not trying to do it for the x values that lie on this line. I'm trying to do it specifically for the car that's floating in space at all these different points. So what would this look like, if I kind of restate what I just said. So we're imagining that we have some curve, okay? And this curve, we're going to call it C, exists right here, okay? And a car is traveling in this direction, okay? And we have some function. Okay, now I'm going to illustrate this, even though this is a two-dimensional function, I'm going to illustrate this in 3D. We have some function f of x, let's say that this function, well, let's make it a 3D function. Let's say that this function is x minus y squared, okay? So this curve is given by the path y equals x squared, right? That's from earlier. That's the curve. And let's say that we have some function, okay? But instead of adding up all the values of this function over a region, I just want to add up all the values of this function over this particular path. Now, what would that look like if we actually do it? Well, if we actually add up all those values, what it's going to look like is, something kind of like this. Okay, it's going to kind of look like a curved piece of paper, if you will. It's kind of bad. Maybe I'll just highlight it. It's just going to look like this curved piece of paper. Okay, it's going to be a really thin piece of paper that lies under this function. Okay, that's kind of what this is going to look like. So it's not volume, it's not area, and this is kind of what a line integral is visually. Okay, so the intuition, right? The intuition is that we are adding up the values of some function, but instead of doing it over a region or an area or over a volume of something, we're going to add up the values of some function over a very infinitely thin curve, or we're just going to say over a curve / path. And we're going to call this path C. Okay, and so that's what it looks like. That is the idea behind line integral. So let's kind of use our brain cells to think, how might we come up with an equation that does this in general. Okay, so let's pretend that we just have this function that represents the heat given off by the car, and we want to calculate the total heat, or maybe it's the energy given off by the car, or the force given off by the car, or whatever it is. Okay, there's a whole bunch of applications we can think of. How do we calculate the total amount of heat or total energy or whatever given off by the car as it's going along this path C? Okay, well, clearly, our first thought should be, well, we're going to add up a bunch of things. Now what are we adding up? We're adding up a whole bunch of values of this function, but what goes here? Do we put like a dx? Do I put a dy? Like what do I go? What goes here? Okay, so that's the part that we need to figure out. And so what this comes down to is we need to go way back in the history books, and we need to remember, how do we approach a problem where our little infinitely skinny rectangles on the bottom there, the base, the width of that rectangle is not dx, it's not dy, it's a very, very, very infinitely small change in the path, right? Or in the arc, right? Or in the arc length is what we call it. And usually we call that ds, okay? So before continuing this example, I'm gonna put a little star here. We're gonna come back to it. We need to talk about what is ds, okay? So let's kind of go over here really quick and talk about what is ds. Okay, so ds, the bane of our existence, okay? If we have some path, okay, it could be any path, but I'll just make a very generic one. Let's just say we have some path C. And eventually, I'm going to be drawing in 3D, I'm going to be drawing these rectangular prisms that are above it that have the width of it is like this small change in our path, right? Because if you really think about it, if I'm talking about the total energy given off by a car, you know, we got to zoom in really, really small. And it's like we're looking at the amount of energy given off as the car kind of travels over some really small distance ds. And of course, when we zoom out, that ds is very, 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 very small. Okay. And so, you know, where is that? What are we talking about? We're talking about, you know, these rectangular prisms here that, you know, add up to our giant sheet of paper, if you will. Okay. And so the question is, what is ds? You know, what is this small change in arc length, right? What is ds, right? We're imagining this is a very infinitely small little change. What is it? How do we talk about it? Because if we were talking about, so this is maybe something to review. So review arc length. Review how to do arc length. Okay, but back in calculus 2, when you were given to like find the arc length from like x equals 1 to x equals 5, the way that you do this is you add up a bunch of really, really tiny arc lengths. Okay, you add up a bunch of really tiny arc lengths. And we said that tiny arc lengths, that was just ds, right? And we said this is the formula for coming up with arc length. And you're like, really? It's that simple? Yeah. The tricky part was figuring out what ds was, because we would have a path. Let's say this path was given by f of x equals x squared plus 1. Okay? Let's say that was our path. And what we needed to do was, well, there isn't a ds in that function. We needed to get ds in terms of dx or dy or something that like we were familiar with. And we said, well, you know, this path is curved, right? If we take like a little bit of arc length everywhere that we go, but we're talking about it on a really small scale, even though the path is curved, these really, really tiny sections of it kind of appear straight. And what's even better is we can break down these little sections into their infinitely tiny components, which should hopefully make some sense that this one would be dy and this one right here would be dx. And that would be the same no matter where we are grabbing our ds from, right? The dx and the dy will change depending on where we are on our curve. Okay? And the idea is that, okay, that's not too bad. So what is ds? Well, ds, using the Pythagorean theorem, ds was just equal to the square root of dx squared plus dy squared, okay? So this really small change in arc length, we could turn it into some terms that we knew about, and we said, okay, if I wanted to calculate the arc length of this path C, all I needed to do was do the integral of the square root of dx squared plus dy squared. Now, even here at this point, this is a little strange because there's a dx and there's a dy, and we only have one integral. What the heck's going on? And so, you know, because like we have a function here, right? We have a curve that's given by that function. Like, what do? I can't integrate this. But we said that our bounds are in terms of x, so I probably want there to be a dx somewhere on the outside. And the way that, you know, we go about doing this is we introduce a very, very sneaky dx over dx here. And the next step is even sneakier, where we are going to put the square root of dx squared plus dy squared here. But I'm going to put inside of this a 1 over dx squared and leave the other dx on the outside. Now, why can I do this? Well, because when you put something, if I were to take this part of this fraction and put it inside of this radical sign here, inside the square root, remember that when you take something out, it goes from a squared down to just one of them. Well, if I want to put something in, it would become squared. For instance, if I had like 3 times the square root of 2, and I wanted to put the 3 back inside of the square root, it would become the square root of 3 squared times 2, or that's better known as the square root of 9 times 2, or the square root of 18, right? So if we want to go backwards and put stuff inside of a square root, we can use this very tricky technique. Now, why is that super cool? Because the arc length here just becomes the square root of, well, if I distribute in that 1 over dx squared to everything, I'm going to get a 1 plus dy dx squared with this dx on the outside. And this isn't so bad because this right here is just the derivative. This is the derivative of our curve C, right? Derivative of our curve C. So for instance, in this particular case, since our function is given by x squared plus 1, now we have an arc length formula, right? So again, let's recap. To find the total arc length from x equals 1 to x equals 5, we're adding up a bunch of little tiny arc lengths. And we said that when you add up a bunch of tiny arc lengths, which are given by the square root of dx squared plus dy squared, we can kind of finesse this a little bit and get the square root of 1 plus now dy dx squared. And for us, the derivative, right, what is the derivative of this function? Well, it's just 2x. So if we square that, we're going to get 4x squared. So we get 4x squared with a dx on the outside. And our bounds, of course, go from x equals 1 to x equals 5. And at this point, we can solve for the arc length. Now, doing this requires a little bit of trig substitution, which I won't do here because that's not the point. The point of this section is to review what does ds represent, how do we kind of manipulate it in such a way that we can actually understand it, work with it in terms of dx's and dy's. And this also translates to 3D very, very, very similarly, except instead of a dx squared plus dy squared, we're going to get a dx squared plus dy squared plus dz squared. So what was the point of doing all this? Let's kind of go back to over here. I introduced this topic of a line integral, which is very similar to all of the integrals we've been doing so far, which is we're adding up the values of some function, but we're doing it over some curve C. And so usually our integral kind of looks like this. And when we add up the values of our function, remember that our function is up here in red, okay, if we're adding up the values of our function over our curve, just like in one-dimensional calculus, we treat these as having a whole bunch of these really skinny rectangles. So if you think about it, adding up all these values simply comes up to adding up all of the areas of skinny rectangles, something that we've done many, many times back in Calculus 2 and also in this class. And so the question is, well, what is the height of the rectangle and what is the width of the rectangle? Well, the height of the rectangle, that's just the value of the function. So that's just my f of x, or in this case, since it's a 3D function, f of xy. What is going to be my ds? Oh, tricky, right? What's going to be my width? Dang it, I gave it away. Shoot, that's okay. So the width is going to be, right, the ds. It's not dx or dy. The width is going to be ds. And so a line integral is typically denoted as the integral over the path of your function times ds. And you're like, okay, this looks super whack. Like, how do I do this? Okay, well, let's do an example really quick. And I will leave this here to try and hopefully so that we don't feel a little scared. So for example, I am just going to say set up the line integral that evaluates. So let's evaluate the function. Let's keep it simple. X minus y. Let's do x minus y squared, make it more interesting. Over the curve let's do over the curve given by, let's just also keep this simple, y equals x squared from x equals 0 to x equals 3, okay? So let's figure out what's happening right now, all right? So in 3D, we have the same thing happening that I just sketched on the other one. We have our curve, which is given by y equals x squared. We are only interested in going from x equals 0 to x equals 3. So we only really want part of this curve. And our function exists somewhere over here. And we're basically just adding up the values of this function specifically over that curve. So we're getting kind of like this very thin sheet of paper that exists over that curve. And so based on the work that we just did, this is the integral over our curve, over our path of our function, right? Because that's the height times the width ds. Now, obviously, we need to elaborate on this. Well, that's no problem. Our function that we're interested in is given by x minus y squared. Wow, very scary, right? So, cool. What is ds? Well, ds, that's a bunch of tiny little arc lengths. That's given by the square root of dx squared plus dy squared. And our bounds, we want to be x equals 0 to x equals 3. So we're almost done with this. We just need to modify our ds a little bit so that it matches our bounds. And based on the trickery that we did before, we're going to keep those bounds. We're going to keep the function x minus y squared. And the ds here is going to turn into the square root of 1 plus dy dx squared with a dx on the outside, okay? And now the question is, what function is this that we're taking the derivative of? Well, this is our path, right? This is the path function. This is this function right here. So it's don't get these twisted, right? This f right here corresponds to the values that we're adding up, but the ds is our change in arc length. So that function corresponds to the y equals x squared. So again, our dy dx here is going to be equal to 2x. And so our very final setup is going to be the integral from 0 to 3, our function, x minus y squared, times the square root of 1 plus 4x squared dx. And we would have to evaluate this. Hip, hip, hooray. Right? Not too bad. Okay. So great. Oh, I have one small hiccup, but that's okay. I was wondering what was kind of seeming off. There shouldn't be a y in here. This wouldn't have a y. Whoops. Sue me. This is what happens when I don't have an example right in front of my face. So you're like, okay, what do I really need to focus on? The concept right now is going to be the important part. So we're still, this right here is the important part. We're just adding up a bunch of tiny rectangles, just like we've been doing, where the height is the function, the width is going to be ds. Great, fabulous, wonderful, awesome. If we have the idea, shouldn't be too bad. Okay, so now let's kind of move on to let's do one more example before we call it quits. Remember, this is just an introductory intuition video, not doing anything super crazy. So let's do one example, and this one I actually have prepared, so hopefully nothing gets too crazy. So let's evaluate the integral, the line integral over of the function 2 plus x squared y ds, where our path c is the upper half of the unit circle. Upper half of the unit circle. Okay, so let's do this. So this isn't so bad. Okay, so we are going to, come back. Okay, so let's sketch our little path, right? So We're talking about the upper half of the unit circle. Awesome. So something like this, okay? And let's say that our path is going this way. We'll talk about the fact that orientation here actually matters, and orientation is the direction that we're going. But let's talk about this. Okay, we know this equation is x squared plus y squared equals 1. However, you know, what's going to happen, the reason why that I ran into a hiccup in the last problem is because if I try to just treat this line integral as saying, okay, well, x goes from 1 or to -1 or -1 to 1. Okay, first of all, going from -1 to 1 would go against the flow of traffic, but let's just pretend that that didn't matter, and we were integrating 2 plus x squared y using the same ds as last time. Okay, integral of dx, oh, actually, we can just skip this part because we already did this. I'll do 1 plus dx over dy quantity squared dx here, okay? And so this dx dy, since this is our path, we would have to solve this in terms of y, right? Y is equal to plus or minus the square root of 1 minus x squared. It's the positive part of the unit circle, so we're going to just simply have the positive square root of that. We'd have to take the derivative, and when all is said and done, this is still going to exist. This y is still going to exist. We're still going to run into some sort of hiccup. Okay, we are going to run into a problem. So how do we avoid this? What's the actual way to do this? Well, hopefully after taking so many lessons in this class, we kind of noticed that this is a circular path, and that it might behoove us to parameterize this path in terms of a single variable. Okay, that is, let's let x equal cosine of t and y equals sine of t, because this is a unit circle of radius 1, for the value where t goes from 0 to what? Well, t goes from 0 to pi. What effect does this have on this entire integral? Okay, so first of all, we can set up the first part. We know our bounds go from 0 to pi, and our function is now parameterized in terms of 2 plus, and we'll have cosine squared of t times sine of t, great, times ds. So we're pretty much almost done with this problem. This is fabulous. The only thing that we haven't taken care of is this ds, which again is the square root of dx squared plus dy squared. Now, the real issue is the fact that these bounds are now in terms of t, right? They're in terms of this parameter t. And our ds is in terms of x's and y's. Boo! But last time, when we wanted there to be some t's hanging around, what did we do? We introduced this sneaky little term, right? We introduced this sneaky little term, and we're going to put that dt squared on the inside, and we are going to evolve this thing. This entire thing is going to now become the square root of dx dt squared plus dy dt squared with a dt on the outside. So remember, we're going to take this, we're going to square it, put it on the inside, and then it nicely distributes to all those terms. And so what of it? Well, now our integral becomes the integral from 0 to pi times 2 plus cosine squared of t times sine of t. And now our ds is going to be this square root of, well, let's see, what do we get? We're going to get dx dt, which is going to be, well, what's the derivative of cosine? Negative sine, but we're squaring it, right? So we get a sine squared of t. And then we get a dy dt, derivative of sine is cosine, and we're squaring that, so plus cosine squared of t dt, and holy smokes, that just evaluates to be, that's just 1, right? And so this entire line integral very, very neatly just collapses into cosine squared of t sine of t dt. And this we can evaluate no problem, right? This is, let's see, the first one is going to be 2t, and the second one, we can use a u substitution here of u is equal to cosine of t, and du is equal to negative sine of t. And so if we kind of do this integral off to the side, we should get the integral negative u squared du, which becomes negative u cubed over 3, which becomes negative cosine cubed of t over 3. So we're going to get minus cosine cubed of t over 3. And we're going to evaluate this entire thing from 0 to pi. This will actually end up working out to be really great. If I put in pi, I'm going to get 2 pi minus, all right, so cosine of pi is negative 1, and that means cosine cubed is still going to be negative 1, but because we're subtracting the minus 1/3, we're going to add it. So add 1/3. This is the first part. And then let's subtract what we do when we get 0. When I plug in 0 into this, I get 0. And when I plug in 0 into cosine, that's going to be a 1. So that's going to give us 1/3. And so we'll be doing 0 minus 1/3 on the inside here. And another plus is going to give us 2 pi plus 2 over 3. And this is going to be our answer. So what does this answer represent? Well, again, it kind of depends on what this function here represents. Okay, it kind of depends on what that function represents. If that function is total, like the amount of heat given off, like let's say this is a wire, and it's a circular wire, maybe on a computer processor board, and this is giving off heat represented by this function at every single point, then this integral over this particular wire, over this path C, is going to, this value represents the total heat given off by this wire, which is kind of some useful information to know if you are planning on doing a computer build and you need to know, like, okay, well, how big of a fan am I going to need to put in here if I'm exerting this much heat from my wire? And I think this is going to be a good place for us to stop. It's kind of an introduction onto how to parameterize certain things. I want to go back and just really quick to this example. Okay, so it turns out this actually wasn't as big of a fiasco as I thought it was, because I had spaced out and completely forgot, and I didn't want to just end the video and cut it. So let me just highlight some things. So in this one, we were evaluating the line integral of this function over this curve. And so we put in the function, we put in the curve, and we got all the way to this point. And I was like, oh shoot, there's a y in there, we're screwed. But it turns out that we're not so screwed, because what is the value of y? What is the value of y? What is the value of this function's y value if we're just hanging out over this curve, right? If we're only talking about the y values associated with that curve, well, those y values are the same ones that are on the curve. They're coming from on the curve. So actually, I could have substituted that out and made the integral from 0 to 3 of x minus x squared, quantity squared, times the square root of 1 plus 4x squared dx, and this would have been the line integral that we would need to evaluate. Now, again, this looks terrible. Ew, discussing, yes, throw up, hack. But that's not really the point. The point is, can we set this up, and do we understand the interpretation of what a line integral is? So hopefully this is enough for us to chew on for a little bit. Sorry for the little mishap. I'll try and put up one more video of one more example of line integrals and stuff, but definitely digest this video. Don't skip over it. This video is supremely fundamental for everything that is about to follow. So watch this video once, watch it twice, and when you're ready, go ahead and move on to the next one, which is going to be line integrals over a path C, but in a vector field.